Have you ever dreamed of seeing the sky dance with shimmering curtains of green, pink, and purple light? The Aurora Borealis, or the Northern Lights, is one of nature's most breathtaking spectacles. For centuries, its ethereal glow has inspired myths and legends, from tales of celestial spirits to bridges connecting our world to the gods. But for just as long, scientists have been captivated by a different question. What exactly causes these incredible light shows? For decades, the precise mechanism remained a puzzle, a beautiful mystery hanging in the polar skies. But now, thanks to incredible advancements in technology and some seriously dedicated researchers, we finally know how the Northern Lights are born. And the story is just as epic as you might imagine, involving a cosmic dance between our planet and the sun. So, get ready to journey from the heart of our solar system to the very edge of our atmosphere as we uncover the science behind this celestial wonder. Before we dive into the deep science, let's take a quick trip back in time. People have been watching and recording auroras for millennia. Ancient Chinese texts describe them as dragon-like lights, while Norse mythology saw them as the reflections from the shields of the Valkyries. Even the ancient Greeks had a name for it, Aurora, the goddess of the dawn. The term Aurora Borealis itself was coined by the famous astronomer Galileo Galilei in the 17th century, combining aurora with Boreas, the Greek god of the north wind. Early observers could only guess at their origin. Some thought they were reflections of sunlight off polar ice, while others proposed they were some kind of atmospheric fire. These early theories were creative, but they lacked the scientific tools to get to the heart of the matter. It wasn't until we began to understand the invisible forces shaping our world like electricity and magnetism that the pieces of the aurora puzzle started to fall into place. The first major breakthrough came in the late 1800s, thanks to a pioneering Norwegian physicist named Christian Birkeland. He was obsessed with the aurora. He even led daring expeditions to the high Arctic to study them up close. Birkeland proposed a radical idea for his time. He suggested that the sun was constantly sending out streams of charged particles, and that these particles were being guided by the Earth's magnetic field toward the poles. He believed that when these particles hit the upper atmosphere, they caused the air to glow, just like electricity passing through a gas in a tube. To prove his theory, he conducted a fascinating experiment called the Terrella, which means Little Earth. He placed a magnetized sphere inside a vacuum chamber and shot electrons at it. And what did he see? Rings of light formed around the sphere's magnetic poles, a stunning miniature replica of the auroral ovals that encircle our planet's poles. It was a revolutionary concept, but it was so far ahead of its time that many scientists dismissed it. It would take decades and the dawn of the space age for Birkeland's brilliant theory to be fully proven correct. The electric currents he predicted flowing along Earth's magnetic field lines are now rightfully named Birkeland currents in his honor. So let's fast forward to today and lay out the complete picture, starting 93 million miles away at the heart of our solar system, the Sun. Our sun isn't just a calm, steady ball of light. It's a churning, boiling sphere of superheated gas called plasma, a chaotic environment of intense magnetic activity. This activity is constantly flinging a stream of charged particles, mostly electrons and protons, out into space in all directions. This stream is what we call the solar wind. It travels at incredible speeds, often exceeding 1,000,000 miles per hour. Most of the time, the solar wind flows relatively gently, but sometimes the sun has more dramatic outbursts. Events like solar flares or coronal mass ejections can release massive, concentrated bursts of particles and energy into the solar system. Think of it as a cosmic storm. And our planet, Earth, is sitting right in the path of this constant stream of solar weather. Luckily for us, Earth has a powerful, invisible shield, its magnetic field, also known as the magnetosphere. Generated by the molten iron core deep within our planet, this magnetic field extends tens of thousands of miles out into space. It acts like a protective bubble, deflecting the vast majority of the harmful solar wind particles away from us. Without the magnetosphere, the solar wind would strip away our atmosphere, making life on Earth impossible. You can visualize it like a rock in a river. The water of the solar wind flows around the rock of our magnetosphere. But the shield isn't perfect. The solar wind is so powerful that it stretches and deforms our magnetic field, compressing it on the side facing the sun and pulling it out into a long, trailing magnetic tail on the night side. And it's here, in this stretched out tail, that the magic really begins to happen. some of the solar wind particles become trapped within our magnetosphere. They are funneled along the magnetic field lines, spiraling back and forth between the north and south poles. As more and more energy from the solar wind pumps into the magnetotail, it becomes increasingly stretched and unstable, like a rubber band being pulled too far. Eventually, something has to give. The magnetic field lines in the tail can suddenly snap back into a more stable configuration in a process called magnetic reconnection. This event is incredibly energetic. It acts like a giant cosmic slingshot, accelerating the trapped electrons and protons and hurling them at tremendous speeds down the magnetic field lines toward the Earth's polar regions. This is the crucial step that was a mystery for so long, the accelerator that gives these particles the incredible energy they need to create the aurora. Now we arrive at the final and most beautiful part of the process. As these super-energized particles from the magnetotail rocket down toward Earth, they finally enter our upper atmosphere, an area called the thermosphere, roughly 60 to 600 miles above the ground. And this is where the collisions happen. The atmosphere here is thin, but it's still full of gas molecules, primarily oxygen and nitrogen. When a high-energy electron from space slams into, say, an oxygen molecule, it transfers some of its energy to that molecule. This puts the oxygen molecule into an excited state. But this state is unstable, and the molecule wants to return to its normal, lower energy state. To do this, it has to release the extra energy it just absorbed. And it releases that energy in the form of a tiny particle of light, a photon. Millions upon millions of these collisions happening at once create the vast, glowing display we see as the aurora. You might be wondering, why the different colors? That all comes down to which gas is being hit, and at what altitude. The most common color we see in the aurora is a beautiful, bright green. This light is produced when charged particles collide with oxygen molecules at altitudes of about 60 to 150 miles. If the particles are even more energetic and hit oxygen molecules at much higher altitudes, above 150 miles, they can produce a rare and stunning all-red aurora. Sometimes you'll see pink or crimson along the lower edge of the green curtains. This happens when the particles strike nitrogen molecules at lower altitudes, around 60 miles up. And what about the beautiful blues and purples? Those are also caused by collisions with nitrogen, but at slightly different altitudes and energy levels. So, when you look at the aurora, you're not just seeing pretty lights. You're seeing a visual map of the chemistry of our upper atmosphere, painted by particles from the sun. And the dancing, shimmering shapes? The curtains, arcs, and rays are all created by the structure of the Earth's magnetic field. The particles are forced to travel along these invisible field lines, so the light they create traces those lines in the sky. As the stream of incoming particles changes in intensity and location, the auroral forms shift and move, creating the illusion that the lights are alive and dancing across the night. It's a dynamic, ever-changing spectacle, directly reflecting the complex and turbulent processes happening hundreds of thousands of miles away in our planet's magnetic tail. So the next time you're lucky enough to witness the northern lights, or even just see a picture of them, remember the incredible journey those particles took. From the fiery surface of the sun, across millions of miles of empty space, guided by our planet's invisible shield, and finally, culminating in a beautiful, silent burst of light in our upper atmosphere. It is a powerful reminder of the deep and dynamic connection we share with our star and the cosmos. Thank you so much for joining me on this journey into the heart of the aurora. I hope you found it as fascinating as I do. If you enjoyed this video and want to learn more about the wonders of our universe, please consider hitting that like button and subscribing to the channel. It really helps us create more content just like this. And if you have any questions or have ever seen the aurora yourself, share your experience in the comments below. I'd love to hear about it. Thanks for watching, and I'll see you in the next video.